This is Daniel Coosbury, and we're going to continue our study of descriptive statistics with measures of spread. Last time we looked at measures of center and how to describe the middle of the data set. Now we're going to look at this idea of spread, which is just about as vague as center, and we're going to need to clarify it. So I've got a couple different data sets on this slide. You can see the histograms look really similar, and we looked at a lot of different ways to talk about the center of the data set. For instance, we talked about the mean as being kind of the average of all the points, and the mode being like the most frequent thing, and the median as being the one like directly in the middle. And frankly, for both of these data sets, your mean, your median, your mode, especially because it's symmetric, end up being around somewhere in this middle bar, around 14, 15, or 16. I just made this data up. It doesn't really have any meaning. But if we're looking for the middle, these data sets have the exact same center. However, they're not the same, and they don't look the same. They look symmetric, but there's just something off. And for instance, this data set starts at 10 and goes up to 20, whereas this one starts at 6, goes up to 26. And so they're not the same, and so we need some other words or terms or numbers to describe, for instance, how these two are different. So this is what we mean by spread. Here the data seems to be more tightly bound between 10 and 20. Here this data is more spread out. There's that word, from like 6 to 26. And there's some other things that spread involves, but mostly when you think of center, you think of where the middle is. Sometimes it's the high thing, sometimes it's just in the middle of the graph somewhere. When you think of spread, think how far is it spread out compared to other ones? Are some closer together around the middle, or are some further away from the middle, like over here? So that's what we mean by spread. So we're going to look at 3 different kinds of spread. The first one is the range. Now the range is a definition you might have seen before. The range of a data set is the difference between the largest and the smallest value. So it's not hard to find. Let's look at this example. The times required for 30 housekeeping workers at a hotel to clean one room are given by these following 30 numbers. So to find the range, all you've got to do is you've got to find both the largest, oops, scratch it out, and the smallest value. Something's a little off. Which means in this data set, all we got to do is pick out, there's the biggest value, 18, and the smallest value is 8. Someone can clean a room in 8 minutes. That's amazing. So to find the range, you subtract the smallest from the largest, and you get 10, and that's the range. Now, the range isn't a very good measure of spread, and we're really not going to use it very much, short of just talking about it. But the reason we don't really like using the range is because it only takes into account 2 data points. So I've given you 30 pieces of data from my hotel, and you've ignored 28 of those pieces, and you've just looked at the biggest one and the smallest one. And you've decided to describe the spread that way, which is fine. However, there are better methods of talking about spread than just looking at the 2 endpoints. We want to measure spread that takes into account all the data. Fortunately, we have that. So let's look at the variance. The variance is a lot more complicated and a little more difficult to find than the range. So what the variance does is it measures how far the values of the data set are from the mean of that data set on average. And I'll kind of show you what this definition means in a second, but this how far from the mean on average. But first, let's look at some notation. So you have the population variance. The population variance is indicated by this sigma squared. So we're talking about a population, and it makes sense that we are using a Greek letter to talk about population. We'll talk about why that's squared in a second, but the sigma squared is the population variance, whereas for the sample, we're going to use a not Greek letter. We'll use the letter S for the sample variance, and I'll talk about why that's S and why that's squared in a little while. What this is saying is you're going to add up some things, but before you add them up, you're going to take all of your data values, subtract the mean. That'll tell you how far they are from the mean. And then you square it to get some kind of positive distance. And I'll show you that in a sec. But you're going to see how far is it from the mean. Then you square it, so you get something positive. Some things are below the mean. They might be negative. But if you square it, you end up with positive things. So take all your data values, subtract the mean, square it, add up all those distances from the mean. So we're talking about how far they are from the mean. So distances from the mean, and then divide by your sample size. That's how you do the population variance. The sample variance is you find the exact same way. You take the deviations from the sample mean. Now there is a difference when you do sample variance, and I'm not going to talk about why it's different in this video. But there is a difference in your sample variance. Instead of dividing by the sample mean, little n, you're going to divide by n minus 1. So it turns out it matters whether you're working in a population or a sample when you're finding the variance. It makes a difference whether you divide by n or you divide by n minus 1. So that's something you're going to have to keep straight. I want to show you on this picture what I mean by the difference, the deviation from the mean. So these are the same data from an earlier slide with the mean cleaning times. So I'm looking at this stuff. So there's my 30 times. But I made a dot plot. That's a nice looking dot plot to show the frequency of each of the cleaning times on here. And there's 30 of them. And I went ahead and computed the mean to be 13.1 minutes of those 30 values. Now, I'm assuming that I'm dealing with my whole hotel and all 30 of my employees, which means I'm not going to think of this as a sample, but I'm going to think of this as a population because I've got all of my employees. I'm not taking a sample of them. So this is my population mean. And what I mean by deviation from the mean, so this red bar is the mean. It's at 13.1. Is for each one of these dots, I'm going to calculate this distance right here. Okay, so this dot's at 14. The mean is at 13.1. So if I compute that distance, I do 14 minus 13.1, I get 0.9. And I'm going to find that for each one of these dots. So for instance, this dot is at 15. I'm going to find the distance between 15 and 13.9, and I get 1.9, and so on. So I'm finding out how far away each one of these points are from the mean. So I can do this from this side too. I can find the distance between, sorry, this PowerPoint getting mad at me. I can find the distance between 10 and 13.1, which ends up being 3.1. It ends up being negative 3.1 actually, because 13.1 is bigger. I'm doing 10 minus 13.1. But for each one of these dots, I'm going to find the distance between the dot and the mean, which is 13.1. And so I'm going to find out that some of these things are really close to the mean, so the deviations are small. Like these are pretty small numbers. Whereas here, 18's really far from the mean, so this deviation is going to be bigger. This deviation is going to be 18 minus 13.1, which ends up being 4.9, I think. Or is it 5.9? I think it's 4.9. And so on. And so I'm going to find all of these deviations. Now, we're not actually going to compute it like this, but this is what the variance is. I'm going to find all the deviations from the means, all the negative ones, all the positive ones. Then I'm going to square them, add them all up, and divide by n. So this is what this formula means. I'm going to find all the deviations. So those numbers I wrote in red, the positive and the negative ones, that's x minus mu. So for each one, I did x minus mu. I did 10 minus 13.1. I did 18 minus 13.1. And then I'm going to square them to make them all positive, so there's no negative things anymore. So it's going to get really big. Then I'm going to add them all up and divide by n. So that's kind of pictorially what I mean by when we mean how far the data set are from the mean, or how far the values are from the mean. You're going to take this distance, how far, square it, add them up, divide by n. So let me show you how this would work if I were to use a table, and I'm going to show you how to do it in the calculator. And you're going to want to do it in the calculator. You're not going to want to do it this way, but I'm going to show you how to do it this way. So this is just a tabular representation of what I did on the last slide, drawing those little red bars and writing. So here are my cleaning times, and I just wrote a few of them on here. Here are the deviations from the mean. So the distance from the mean. So this one's bigger than the mean, so that distance is positive. This one's a little bit less than 13.1, so it's negative, and so on. So you find all the differences from the mean, and then you square those things. So now they're all positive. See, that's positive now. It's tiny, but it's positive. And then once you square them all, you add them all up. So this is my sum. This is my sum of all the deviations from the mean. So I could write this as the sum of all my xi's minus mu squared, which is in the top of the formula for, it's this thing right here, the top of the variance formula. So once I have that, I find the variance by taking that number, divide it by big N, because I'm dealing with the population. I get this as my variance, the 7.98. So that's the long way to do variance. I'm going to show you the short way to do variance on the calculator in a little bit. But that's the general idea is what the variance is it tries to describe how far away the values are from the mean, and it does it with every single value. So it's much stronger than the range, which only uses 2 values. This one used all 30 values. So you take all the data into account to describe how far it is from the mean. And that's a number used to describe how spread out the data is. It's really nice, and it's really powerful because it uses all the data, not just 2 things. So that's the population variance. I want to show you a sample variance one real quick, because the sample variance, as you remember, is a little bit different. You're still taking deviations from the mean, the sample mean this time. The sample variance you're dividing by n minus 1. So I wanted to show you an example of that. So we have a company that manufactures batteries, and they're testing a new type of battery designed for laptop computers. They measured the lifetimes in hours of 6 batteries, and the results are these 6 numbers right here. We want to find out the sample variance. So we're not dealing with population anymore. We're dealing with the sample variance. Oh, thing went away. Let me get it back. Okay, so here's your sample mean. You add them all up, divide by 6. You get a sample mean of 4. And then you would find each one of the sample variances, each one of the deviations, and then square them. So for 3, I'm going to subtract the mean and square it. For 4, I'm going to subtract the mean and square it. For 6, subtract the mean and square it, and so on and so on and so on. And you end up with this number as your sample variance. Notice in this case we're dividing by 6 minus 1, not by 6. We're doing this is n minus 1 rather than n, which is important when doing the sample variance. So this is n minus 1 rather than n. So we're doing 5 instead of 6. Okay, now you got, let's talk about this is the last measure of spread we're doing. It's called the standard deviation. Now, why we need a standard deviation when the variance is already computed? Let's look at this sentence up here. When we compute the variance, we end up squaring all of the deviations from the mean, which you saw that. We made them all positive. And when we square them, this causes the units for our data to become squared. So for instance, in the cleaning problem, we're talking about how quickly you can clean in minutes. Well, when you square it, you have square minutes. And I don't know what square minutes are. Like I can't speak about square minutes. It's not like square feet where it makes sense. When you find the variance, it turns out you're squaring the units because you're squaring all the deviations, and it makes the variance somewhat hard to interpret. So what the standard deviation does is it takes the square root of the variance. So basically you go through all the trouble of finding the variance, and then you square root it, and you get your units back, and you get a smaller number. So when you square it, your deviations are blown up. When you square root it back, you have the standard deviation, which has the same units as the data, and your data is not, your deviations aren't as huge because you square rooted it. When you square root bigger numbers, they get smaller. So these are the oops, I messed something up here. These are the formulas for the standard deviation. So for the population standard deviation, you find the variance for the population, then square root it, or you can write this formula this way. So find the population variance, square root it. For the sample one, you find the sample standard deviation. Oh man, there should be a 2 there. You find the sample standard deviation. Find the sample variance and then square root it, and you can kind of write it like that. So the nice thing about these 2 things is if you have the variance, you can find the standard deviation really easily. All you do is square root the variance. If you have the standard deviation, you can find the variance really easily just by squaring it. So if I know, for instance, what S is, that's my standard deviation, then I do S squared, I get the variance. That's easy. Just square that number. So that now you see why the sample standard deviation, we use S. It stands for standard deviation. So that's why we use little s. We use S squared for variance because it's the standard deviation squared. So that's the variance thing. We don't have a special letter for it. We just do S squared because you just square things. We use sigma for population standard deviation because sigma is the Greek letter for S. So that's nice. Kind of like M, you use the Greek letter for M. And then you square that to get the variance. So that's the variance. That's the standard deviation. That's the standard deviation. That's the variance. Well, that's not writing. There we go. So anyway, the nice thing is once you have one of these, you just square it or square root it to get the other one. So for instance, here are the exact the examples that we already did. This is the variance of the cleaning times. This is in minutes squared, which doesn't really have a meaning to me. So what I'm going to do to get the standard deviation, I just square root that, and I get 2.83 minutes. So my standard deviation is now interpretable because it's in minutes. It's not in minutes squared anymore. So I can say the standard deviation of our cleaning times is 2.83 minutes. In the same way, with our battery life ones, our variance is 2. This was in hours, I think. So this is hours squared. And I like square minutes. I don't know what square hours are. But if I take the standard deviation, I take the square root of 2, and I get 1.41 hours. And now that's something I can understand, like 1.41 hours. It's a unit that makes sense. So that's my sample standard deviation. Okay, I don't think I've showed you how to do this in the TI yet. So let me go back to this problem, and I'm going to pull out my TI, and I think I saved this data somewhere. So I'm going to do this real quick. This is the battery problem. So I'm going into stat edit, and my data's gone. Let me put this data in real quick. So I'm going to do 3, 4, 6, 5, 4, and 2. So these are my battery lives, and I want to find the sample variance of these lifetimes. So I'm going to find the sample variance. What I'm going to do, just like with finding the mean, I'm going to go to one variable stat and do L1 as my list and not have a frequency list. So make sure there's nothing there. And when I do one variable stats, look, I got my mean again, which is great. And now I've got 2 things down here, and both of these things have to do with the standard deviation and variance. And this is just kind of worth remembering. When you look at this SX, the S means you're looking at the sample standard deviation because that's S, not sigma. The sigma X says you're looking at the population standard deviation. Both of these are standard deviations. This is for the sample where you divide by n minus 1. This is for the population where you divide by n. So it's probably worth noting, let me get my pointer, that in your calculator, you're looking at when Sx is your sample standard deviation, whereas sigma x is your population standard deviation. Now what I want is I want my sample variance. So here's a good question. If all I have is my sample standard deviation in my calculator, which was 1.41. So it said that Sx is equal to 1.41. We should say S is equal to 1.41. So don't use the calculator notation, use good. But if it says this, my sample variance is just S squared. So the calculator gives me one of these 2 things. It gives me the standard deviations. I've got to pick it based on whether I'm working in a sample or a population. I'm working in a sample. So then my sample variance is S squared, which is 1.41 squared, which that's just the square root of 2. So that's 2. Or if you do it in your calculator, it's like 1.9 something or other, but it's basically 2. So here's kind of the takeaway. Your calculator won't tell you what the variance is outright, but it will tell you the sample standard deviation and your population standard deviation. So if the question is what's the standard deviation, your calculator spits out that number. If it's what's the variance, take one of the standard deviations, take the right one, and then square it, and you got your variance. So your calculator won't tell you the variance outright, but you can find it really quickly just by squaring the standard deviation. So that's my takeaway. Okay, last thing. Just like with finding the mean with grouped data, we can find the mean, we can find the standard deviation or the variance with grouped data as well. And I just wanted to show this to you. You may see this a lot, you may not. But if I don't have a data set, but I have grouped data, I can find the standard deviation or the variance in the same way I found the mean. If you remember, the method for finding the mean with grouped data is you want to put your class midpoints in the first column and your frequencies in the second. So bear with me while I do that real quick. My midpoints are the numbers that are halfway between the lower limits and the next lower limits. And my frequencies are the numbers in the second column. And if I go out of there and go to one variable stat, this is in the newer ones, I do L1, frequency list is L2. Remember in the old one, do L1 comma L2 on your home screen. Hit calculate. Suddenly I get my standard deviation, and I'm dealing with a sample. So my standard deviation is a 77.3. So the S1 is my sample standard deviation. It's my estimate one. And so I can report based on this group data that my sample standard deviation, which is S, is approximately 77.3 messages. And that's in units, the message unit, not square messages. So it's really easy to find. Just remember that's a thing and remember how to find it. The calculator is really powerful, and we can do things like estimate standard deviation, variance, or whatever with it. So those are the 3 different kinds of measures of spread.